Alright, typically speaking, vectors, because they're defined by both magnitude and direction, those are the two basic components, so I've made a note of that here. They're usually defined by magnitude and direction, so they're usually written out in what we refer to as direct notation, using, in this case I'm using the double bracket symbol. Sometimes they'll just use single bars on either side, but notice that this is a different statement than this here. This is the vector v, and it is composed of the magnitude of v and the angle, the direction angle for v. And we mentioned in previous videos this theta here is measured from the positive x-axis counterclockwise. There are other ways to talk about angles for vectors, which we may see in future videos, but for the moment, this is where we're going to sit with that. And at the top here, you can tell our goal is going to be to break this down into component form. Now, we've already discussed in the last video about how to find a direction angle, and that was if you were given component form. So really we're going to be kind of working backwards with this to go in the other direction. And then here, with the magnitude, if we had component form, well, it'd be easy enough to use the Pythagorean theorem to get the magnitude, which we saw in the video before that. In this case, though, we're going to be saying, well, and we talked about this in a previous video, so this will be a quick little reminder, that we're thinking about this as a right triangle, and let's suppose this is our theta, and this is our v. In order to achieve component form, in order to get component form, we need to get this Vx measurement and this Vy measurement. It's going to turn out, thankfully, that for all of these problems, that our component form, this Vx and Vy that we're looking for, are going to be found by using right triangle trig, just like we've done in the past. But instead of using tangent, like we did the inverse tangent to find the angle, we're going to be looking at sine and cosine. Because notice that our Vx is the adjacent side of this triangle relative to this angle, and our V hat up here, the whole original resultant vector, is our hypotenuse of this right triangle that we've created. And I guess appropriately these would have little arrows going this way. All we're going to do is say, well look, in order to find Vx, we're going to take the magnitude of v and multiply it by the cosine of theta. And then to find Vy, because it's using the opposite side now, we're going to switch over and we're going to use the magnitude of v times sine of theta. And if you're not sure where this comes from, just keep in mind our basic sine, cosine, and tangent ratios normally would set this up as cosine of theta equals Vx over the resultant v. And so what I'm doing is I'm taking that magnitude that's down here on the bottom and I'm multiplying it up to this side. The same thing is true for sine of theta. This is what I was mentioning about opposite and hypotenuse, is that Vy compared to the hypotenuse is sine of theta. So we'll just take this guy off the bottom here. We're just bringing these guys up here. This is kind of what I'm getting at. Just bringing them up here. And that's how we find Vx and Vy for our component form. There will be a video for each quadrant, potentially, or maybe I'll pair them up, and the idea is going to be that you can tell that thankfully our calculators will be able to handle this a little bit better than they did with tangent. That's a good thing.